This is example 2 from 1.2. And basically, it's just looking at a little more in depth. And instead of just doing a reflection, we're going to see that we can do transformations that involve stretches as well. And it is important that all we're really doing is making sure we're identifying our parameters. And if we go from, and I just want to write this, that the graph of f of x that turning into g of x requires us, in this case, to vertically stretch by 2. And the reason for that is the a value is 2 in this case. Now, if we vertically stretch by 2, then what's happening is a point on f of x is going to turn into that same point, but we will multiply the y by 2. And that's really important that this point then would be on the function g of x, and we could connect those points. So with discrete shapes, which we get quite often, we can find what I would typically call maybe vertex points. And if we look at that w, which is probably the language that they'll use, is that those first two columns, these right here, create the coordinates. So just looking at this point, and it's probably the only one I'll write on here, that this point is at -6, 4. So if we picture what our mapping is doing, is it's taking the specific point -6, 4, not changing the x, but multiplying the original y value by 2. So instead of -6, 4, I'm going to have the coordinate -6, 8 on g of x. Now, they show that in the table, but they are just showing that for the input of -6, so we would still be putting -6 into the function, on g of x, we get an output of +8. And all that's happening in this table is all of the y values are getting multiplied by 2. Now, what's very, very important is that there is what we call an invariant point. And where this invariant point is occurring is where the transformation does not affect the point. And there's two locations, and I should have started both, oops, is that we are getting the 2 points wherever y is equal to 0. And the reason for that is 0 multiplied by anything, be it +2, 1/2 later on, -1 in the previous examples, that's not going to change. And so those invariant points are the points that have not moved. And a lot of students make the misconception that invariant points are points where the original and the transformed intersect. That's not always the case. Well, I shouldn't say that's always the case. That is true, but that is not a requirement for the invariant point. The invariant point is that the point cannot have moved. And intersections are sometimes just that, a coincidental intersection. So for this particular graph, there are two invariant points, -2, 0, and 2, 0. And I'm just going to kind of summarize that underneath. So we need invariant points, and we need to state the domain and range, which would be nice and relatively easy. So we're going to do that for f of x and g of x. And then over here on the right, I'm going to identify the invariant points. And there are two. The invariant points are -2, 0 and 2, 0. They are invariant because of their y value of 0, because 0 times anything, and I'll put a there, is still 0. So it's unaffected by that vertical stretch. All right, domain and range, everybody's favorite, I'm sure. The domain of f of x, that's my blue W on my graph, is that x is greater than or equal to -6, less than or equal to +6, and x is an element to the real. We'll do the range at the same time. For the y variable, it must be greater than or equal to 0, less than or equal to +4, and y is an element of the real. Now, really important to stress this, that to go from f of x to g of x, I did a vertical stretch. Now, I hope logically that we didn't affect the horizontal. And if you take a look at the extreme values of x, we see that they are the same for the blue and the red graph. So the domain is unchanged. The domain is still that x has to be greater than or equal to -6 and less than or equal to +6 and is an element to the real. For y, however, 0 is still the lower bound. It's the lowest value, but now the upper bound has become twice as much, and that becomes 8. Now, it is worth mentioning that the range and domain, for that matter, are coordinates from the graph. So if I multiply every y coordinate by 2, then we see that our y values get multiplied by 2 as well. Now, this is one of those annoying, maybe, I don't know what exception is the right word, but 0 times anything is still 0. So we see that our lower bound stays at 0 for that particular question. Okay, looking at the next one, what they're doing is they're changing the value. And I want to write this out again, that if we look at f of x and turning it or transforming it into, oops, we'll erase that. That's going to look weird if I don't. If we turn that into g of x, then the way that we do that is, in this case, a vertical stretch by 1/2. Or again, trying to push that mapping as we go, is that x comma y turns into x comma 1/2 y. Now, if you did write that 1/2 as a decimal, that's perfectly acceptable. Just be careful with those, non-terminating, non-repeating decimals, because they can be a little bit trickier to work with. Now, it is important we are transforming the same original function, and function notation becomes very important for that the original function is the same w. But what we're doing instead of multiplying y values by 2 is we're multiplying them by 0.5. And so my new w is, and we try not to use the words expanded and compressed. That's part of the old curriculum. We stay away from that. But essentially the idea is that a vertical stretch by 1/2 halves the distance that the point is away from the x-axis. And if we take a look at this point right here, again, this was at -6, 4. It has been transformed into -6, 2. And the way that we do that is my y value gets multiplied by 1/2. So 4 times 1/2 is 2. All right, to finish that question off, we're just going to talk about domain and range. It is going to be very, very similar to the first technique that we use. I'm going to identify f of x and g of x. You can probably just look up and look at the domain of f of x. The one thing that I want to do to try to make this a little bit clearer is I'm going to use interval notation. And interval notation is you write the variable with a colon, and then you write the lower bound or the minimum, really the same thing. And then you write the upper bound. Now, I am going to write both for this question because we have to get used to what this looks like. The other piece that's important is if we use a square bracket, it's less than or equal to or greater than or equal to in this context. And if we use a round bracket, it is just less than. All right, so the square bracket represents, that it can include the endpoint. The round bracket indicates that it has to be less than or greater than that endpoint. So for f of x, I'll write that with the inequality. The lower bound is -6. The upper bound is +6, and x is still an element to the real. So in our interval notation, x exists from -6 to +6 and is an element to the real. The advantage of interval notation is that it is always done the same way, whereas every inequality can be written in a different direction. And I'll show that above in red to try not to make it confusing, that I could also write this as x is greater than or equal to -6 and less than or equal to 6. That red line and the black line mean exactly the same thing, whereas in interval notation, there is one way to write it, which I think is a big advantage. All right, again, for the range, and I'll do both, the lower bound is 0, the upper bound is +4, and y is an element to the real. In interval notation then, y exists from a square bracket on the 0 to a square bracket on the 4 and is still an element to the real. All right, just getting this out of my way for g of x. Really importantly that we've done a vertical stretch, so the domain hasn't changed. So x still exists from -6 to +6 and all the real numbers in between. The y though, and taking a look at this red, I'll just scroll up a little bit here, the red w has a maximum value at y equals 2 and a minimum value at y equals 0. Every point on that red w exists between those two bounds. And so that becomes our new domain. Now, yet again, I am simply multiplying these numbers by the stretch. So my y exists from 0 to +2 and it's all the real numbers in between.